Okay, to make sure we can get through this, because things always seem to take longer online, I wanted to go ahead and make a video for these last few questions about power, rather than teaching them live, just to make sure we're all good with it. So what we left off with yesterday was talking about power when we're not changing our speed, when we're not changing our height, is based just on your internal energy. When there's no change in speed, there's no change in velocity. There's no change in kinetic energy. When there's no change in height, there's no change in potential energy. So the work is based just on your own internal when there's no change in height and no change in speed as well. What we're going to talk about now is when we do change the height, even if you are expending energy for the same amount of time, when we change the height, obviously, because you know this, because you probably experienced this, you feel more tired, right? Even if you walk the exact same distance for the exact same amount of time, going up an incline versus a flat surface, you have to overcome that potential energy, basically. So what's going to end up happening here is that we're going to have to, in addition to just the basic energy that we have to use to walk a flat surface, we're going to add to it the potential energy you have to overcome. So what we found from the last question, which again was just plugging in the power that we were given that this guy can use, and then finding the time based on the distance. The power and the time is still going to be the same as well because it's still the same speed and still the same distance. So again, to find that time, just to remind ourselves, the time, it's change in time, but it's just the total time. It ends up working out the same way. Ends up being distance over speed. So it ended up being 2,000 meters. Oops. It ended up being 2,000 meters, 2 kilometers, right? Over 2. So our time ended up being 1,000 seconds. So we had that. Now we also had was, again, the energy you had to expend from just traveling this flat surface was 250,000 joules. Now, what we need to find is the additional potential energy we're going to have to add to this that you have to overcome. And again, that energy gets exerted in your own body. So it's the same distance of 2 kilometers. I'm going to go ahead and write this as 2,000. But the hill is now inclined at 3 degrees. So not a super steep hill, but that's going to matter here. So we need to know, again, this is going to be a change in potential energy because now our height is changing. There's no change in kinetic energy. You're maintaining the speed. So again, we are going to add to this the potential energy that we, the change, and potential energy that we're going to have to overcome here. So I want you to take a moment because I really hope you know how to do this by now. It's okay if you don't. But our change and potential is U final minus U initial, which is going to be, if we're starting down here, we can call this our initial height. And this is, oh shoot, let me bring it back this way. Careful with this. This is our initial height. This is our final height. So take a moment. One of these is going to be 0 if this is our initial height. One of these we're going to have to find the height for because 2,000 meters is not the height. That's the distance traveled. We need the height. So take a moment and try this. Okay, so we should know, hopefully by now, we're getting better with this. I hope that understanding when certain energies are 0, our initial potential energy is 0. If our height is 0 initially, our potential energy initially is 0. So for our final, we need to do mg times the height we end up at. So in order to do it, we need to do some trig. So our height is over here. This ends up being a sine function. Sine 3 equals height over 2,000. We end up multiplying the 2,000 over, and we get height is 2,000 sine 3. I forgot to grab my calculator before I came over here. Give me one sec. Okay, you should get 104.67. So this is the height we're climbing to. So again, we're going to have to overcome all that potential energy. I'm going to drop this down. Our change in U is, again, U final minus U initial, but it ends up just being U final. Our mass of this hiker is 50 kilograms. Gravity is 10. Our height is 104.67. 50 times 10 times 104.67. We end up getting 52335 joules. So the energy now that he has to expend, we're actually going to add this. His internal energy is what we found before. This is just flat surface, right? So we're going to find that first. If there was not an incline, what would be the energy? And then we find the potential energy he has to overcome. So he's going to have to exert more energy, and this is our answer. This becomes, let's see, 300,002. Make sure I'm doing this right. Yeah. 335 joules. So this is our answer. So again, you're going to try it again on the next question. What you're going to do is solve the problem as if it was a flat surface, just traveling at a constant speed. So we're not concerning ourselves even with the speed at all. And then we want to find the additional energy we would need in order to overcome that change in either height or speed. So just as a hint here, in this question, once more, because he maintained the same speed, but the height changed, we only added on the additional potential energy. Say, for example, that the height changed as well as he wanted to increase his speed. We would need to add that change in kinetic energy as well. So in this next question, we'll go ahead and we'll read this, and then I'll give you guys a chance to try it. A 65 kilogram runner can produce 450 watts of power on average. How much internal energy must he use if he wants to increase his speed from 3 meters per second to 5 meters per second on a flat surface? So looking at this question, think for a second. What additional energy are we going to have to overcome? A change in kinetic or a change in potential? This is going to be a change in kinetic energy. We're trying to increase the speed. So we need to find, first off, what we're going to find is we're going to use this general formula. Now, again, we're going to go ahead and first find just E internal, just addressing this as if it was a flat surface that we're not increasing our speed. So all we have to do to start with to find E internal is plug in power, plug in time. Once we get what E internal equals, we are going to add our our change in kinetic energy to it. So again, I'm going to kind of write some steps out here for you. Step 1, plug in above to find if we didn't have to deal with a change in kinetic energy, if we didn't have to deal with a change in the height, and again, we're not dealing with that here anyways, plug in just the base, the power, and the time to find change in E internal. Step 2, because we're trying to increase our speed, find the change in kinetic energy based off of this change in speed. Keep in mind here that K final minus K initial, we're going from an initial speed of 3 to a final speed of 5. So when we do K final minus K initial, neither of those will be 0 because we have an initial speed, we have a final speed. Once we can find that, then we can add our change in E internal plus the change in K. Go ahead and give it a shot. Okay, so again, what we're going to do to address this first is we're just going to think about this as if there was no other energy we had to overcome. So this person, typically, if there was no other kind of things going on here, can exert this much power, And thankfully, it's already in seconds. So we didn't have to do any conversions there. I made that at least a little bit easier. So we have 5 seconds. So we got 450. This is step 1. Equals the energy that he's going to have to use divided by the time, which was 5. So all we got to do is multiply that 5 over. We get change in E internal. Let's see. It's 2,000 plus 250. Is that right? Yeah. So this is how much energy. If we didn't have to worry about an increase in speed, that's how much energy this guy would have to use. Not a ton. Yeah. However, we now have to overcome this change in kinetic energy as well. So we're going to now find how much kinetic energy he will have to kind of use up or overcome to change from 3 to 5 meters per second. So this is our initial speed. This is our final speed. So coming down here, change in K equals K final minus K initial, which is 1/2 mass times V final squared minus 1/2 mass times V initial squared. We've got 1/2, our mass is, what did we say? 65. Our speed final is 5 meters per second squared minus 1/2. Our mass is 65. Our initial speed was 3. Let's go ahead and plug this in. We got 0.5 times 65. It's 5 squared. Where's my square button? There you are. Minus 0.5 times 65 times 3 squared. Okay, we should get 520 joules. So this is a lot smaller because speeding up is not nearly as exhausting as going uphill for as long a period of time as our last guy was. This is only a period of time of 5 seconds. Our last guy was going for 1,000 seconds. So keep that in mind because you're like, whoa, we came up with a lot more energy here than we did here, right? This ends up being, again, 520, which is just, let's finish this off and then I'll kind of keep talking, which is just going to get added to our internal energy. So we are adding the internal energy. If we didn't have to do anything, if it was just a flat surface, we're not increasing our speed, plus now we're trying to increase our speed. So we have 2,250 plus 520. So yes, this is a much smaller answer than before. What is this, 2,800, I think? Yeah. But keep in mind, our time was only 5 seconds, and we're just increasing our speed a little bit here. Versus we increased our height here by 104 meters, and we were going for 1,000 seconds. So that's a lot more energy you're going to have to use in this case, rather than still on a flat surface and only going for 5 seconds. Okay, there is one more type of power question you're going to be looking at. So we're going to kind of do just a little bit of note right here, and then we'll try 2 more questions, and then we're done. So there are some questions where you're talking about the power being transferred into an object by a single force. So these questions you're talking about, we're talking about the energy that somebody has to expend inside their body, like an actual person. These questions, we're talking about, excuse me, there we go. These questions, we're talking about typically the power, the total power of pushing something or pulling something. We are kind of transferring power into that object because now that object is in motion. That object has energy. So even if I am pushing something, what we're talking about in this question is, yes, how much power we're generating, but that power then being transferred to the object, yeah, because now that object is in motion, that object can do work and have energy. So we use a single formula for this. We talked about this yesterday, but this is the force times the speed. We have to be very clear here. In the textbook, it says F cosine theta. We've talked about this. The reason why I don't like that formula is because they give you an angle, and sometimes that angle can change that you have to use in the formula. So all you have to remember here is we need the force component. F is the force component in the direction of motion. You might have to do some trig. If you have an angle, you have to find the force component in the direction of motion. Let's go ahead and look at example 1. A man pushes a block horizontally with a force of 50 newtons for a distance of 5 meters in 10 seconds. How much power did he transfer to the block? So this one's pretty easy because he's pushing it horizontally across a flat surface. Therefore, this force is in the direction of motion. This is good. We can just use that power equals FV. We don't have to do any trig here because he's pushing in the exact direction of motion. So we have the force, right? The force he pushes with is 50. We have to know the speed. So he's going 5 meters in 10 seconds. You guys should know how to find the speed off that. Go ahead and try it. Okay, 5 meters in 10 seconds, guys, that is the speed, right? Speed is distance over time. So this is only 0.5 meters per second. So super easy from here. We have the force, we know the speed. Go ahead and plug it in and solve for power. Okay, power equals, our force is 50, our speed is 0.5. We get the power is then going to be 25 joules. Half of 50, right? So again, that block now has power if that box came up against some other thing. It can keep going, it can keep doing work and expending energy. That block now has that same power as well that you are putting into it. I'm done. 25 joules. Oh, sorry, 25 watts. Careful, I almost made that mistake. Energy is in joules, but power is in watts. Because again, power is energy over time. So it's a new unit. Okay, let's go ahead and try the next one. So this one is going to be a little bit different now because we do have an angle. So when we go ahead and plug in, we got a man pulling on a crate with a rope. It's got a force of 90 newtons at an angle of 30 degrees. The distance is 20 meters in 1 minute. So what we need to find for F is the component of this force in the direction of motion. I know it's been a while, but we should know how to find, if this is the direction of motion, to find that component. So once more, we're going to need to find F. You're going to need to find V. Be careful with the conversions here. It needs to be meters per second. Go ahead and give it a shot. Okay, so to find F, this is the component in the direction of motion. We can go ahead and call that force X if you'd like to, because that is the X direction. So that's going to end up being, because Fx is the adjacent, you should have ended up finding out that it ended up equaling 90 sine 30. Obviously, again, you can set up your whole trig function, multiply the 90 over, go from there, but I just know that's, oh, sorry. Oh my gosh. It's early. Cosine, because that's the adjacent. Good Lord. 90 cosine 30. Okay, so the force component in the direction of travel is 77.9, sure, newtons. And our speed, we are going 20 meters in 1 minute. Be very careful. I hope you went and got that as 60 seconds. So we have 20 meters for 60 seconds. I should know what this is. 0.33, right? 0.66? Oops. I was right, 0.33. So 0.33 meters per second. So we have the force component, we have the speed. We've got Fx equals 77.9. We've got that the power equals F in the direction of motion times our speed. We've got 77.9 times 0.33. We should get 25.7. What's our units here again? Watts. So again, now that crate has some power as well. It's in motion. It can do energy, or it can expend energy. It can do work. I know it sounds a little confusing the way it says transferred to the crate. Really, it is the power you are generating that is being transferred to the crate. So we're going to try some practice problems again with this. You guys will work together. The power questions actually don't get much harder than this. This is as simple as it gets. It's really those work problems that you guys need to make sure that you have down for the test.